Okay, hello. We are now into Unit 3. So we've covered rates of reactions, we've talked about equilibria in reactions, and we talked very briefly about entropy of reactions. We're going to come back to that a little bit more. But for the next couple of chapters, chapters 15 and 16 in the textbook, we're going to really focus on equilibria. We're going to talk about acids and bases and how these equilibria, um, how we control them in acid and base reactions, and what they tell us about which reactions are likely to occur and how we can monitor them and all this other kind of fun stuff. So we're going to talk about acids and bases today today. As you're watching this particular video, we're going to define some terms. Um, we're going to define what we consider an acid, what we consider a base, and we're going to look at water in particular, because of course water is neither an acid or a base. And so that gives it some really interesting properties that we're going to take advantage of when we talk about weak acids and weak bases. So we're going to define some terms. We're going to talk about water. And that's where we're going with this one. Okay, so first of all, let's define what we mean by an acid and a base. So there's a couple of different definitions out there. We are going to use the Bronsted-Lowry version. Definitions, and we'll start with the acid. So the Bronsted-Lowry definition of an acid is something that when you react your Bronsted-Lowry acid, so this is going to be our HA, this is our acid. When you react it with water, you get a transfer of an H plus from the acid to water. So water adds an H plus and becomes H3O plus. This is called the hydronium ion. And you get A minus, right? So this acid has lost its hydrogen and has become negatively charged, and we call this the conjugate base. Right? So we have an acid, we have a conjugate base, we have water, and we have a hydronium ion. So if you see any kind of reaction that looks like this one, right, something plus water gives you hydronium plus a conjugate base, that something at the beginning is an acid by the Bronsted-Lowry definition, which is the one that we're going to use for the most part in the course of this class. All right, so now we need to define what a base is, Bronsted-Lowry definition of base. And we're going to do the same thing. We're going to react our base, whatever that is. So let's have it be B for base with water. And what happens when we react water with a Bronsted-Lowry base is the opposite thing. So in an acid, the water added an H plus atom. In base, water will remove an H plus atom. So water will become hydroxide. Oh, this is our base. I guess I didn't write that down. So water will become hydroxide, and that means that now our base has added an H plus, and so we end up with a positively charged thing over here, and this is a conjugate acid. So now you'll notice that your conjugate acid, you have an acid on this side, so the base becomes an acid when you add H plus to it. And think about this, if you reacted this compound with water, what's going to happen? It's going to give up that H plus and become, right, and make a hydronium ion. But that's not what's happening here because we're under basic conditions, and so we're creating OH minus and whatever our conjugate acid is. So these things are the key, right? If we see H3O plus in our solution, the presence of this indicates that we have an acid, right? Indicates acidic conditions. And in the same way, likewise, the presence of OH minus indicates basic conditions. So this is one of those ideas that we're going to use a lot, right? We're going to say that when we are under acidic conditions, we're going to have the hydronium ion present. And how much hydronium ion is present is going to tell us how acidic the solution is. And we'll get to that when we talk about pH scales. Similarly with OH minus, however much hydroxide is present, the more hydroxide that's present, the more basic our solution is going to be, right? And so more OH minus equals more basic solution. More H3O plus equals more acidic solution. And the reason that all of this is true is because Bronsted, Lowry, when they came up with these definitions for acids and bases, it works really well because we use water as kind of our standard. And so if it reacts with water and creates hydronium, it's an acid. If it reacts with water and creates hydroxide, it's a base. And so we're going to use those definitions going forward. So make sure that you're comfortable with those, and we'll move on to the next video. I think I'm going to switch the water stuff into the next video just to keep everything kind of reasonably timed. So in the next video, we'll talk about water, because you'll notice that water has acted as both an acid and a base in these two reactions already. So it's kind of switched its role. And so that's something that's probably worth a little bit more discussion.